Hello, good morning. Today let us solve some problems displaying both explicit, implicit and also derivative boundary conditions. Okay. So, let us start with the Crank-Nicholson scheme which is a implicit scheme. Okay. So, I start with example 1. So, initial conditions, boundary condition, and choose h equals to 4 and lambda equals to 1. This is for calculation sake. In general, we may not choose such a huge step size. Okay. Compute u at first time level using Crank-Nicholson scheme. So, this is a problem. Okay. So, let us solve this using Crank-Nicholson scheme. Okay. So, the Crank-Nicholson scheme okay. So, as you can see, this is implicit, all the time levels, higher time levels are to the left and the past time levels are to the right. Okay. So, now in the present case we have lambda equals to 1. So, accordingly the scheme reduces to so the middle term gets killed because of 1 minus lambda term. Okay. So, now this at j equals to 0 we have okay. Now, our initial condition this implies equals to 2 and boundary condition. So, this implies 0 j equals to 0 and u of 20 t equals to 10 implies. So, our grid is x 0 is 0, x 1 is 4, x 2 is 8, x 3 is 12, 16. So, this implies u 5 j is 10 because we need at the boundary point. Okay. So, this is because h equals to 4. So, now let us write down the equations corresponding to I equals to 1. Okay. So, our equation is minus okay. So, now let us write I equals to 1. So, the equation will be okay. So, then I equals to 2 because what are the unknowns? Unknowns are this is x 0, x 1, x 2, x 3, x 4, x 5. Since there are no derivative boundary conditions, the unknowns are at these grid points. Okay. So, I runs from 1, 2, 3, 4. So, 1, next one is 2, this will be I 2. So, then I 3, then I 4, okay. So, now let us look at the values u 0 1. So, we have also discretized and obtained the, so u I 0 is 2, u 0 j is 0, u 5 j is 10. So, let us record these values. We also have u I 0 is 2, u 0 j is 0, u 5 j is 10. Okay. Now, for u 0 1 comes from this. So, this is 0. Okay. Then this is unknowns are as I mentioned u 1 1, u 2 1, u 3 1, u 4 1. Okay. So, u 0 0, u 0 0 we have this is a for j 0, if you recall this equation when we have written for this. Hence, we have to use this value not this value because this is from I. Okay. We are running the equation from I 1. Okay. So, this and u 2 0 is 2. Okay. So, this is how the equation gets reduced. So, 1 0 and 3 0, these all are 2, this is 2, this is 2. Okay. and here we have phi 1 which has to be taken from here. Okay. So, accordingly the system simplifies to so this will be 12. So, we can solve this. Okay. This is a tridiagonal system and we can solve. So, I have pre calculated values. So, I am not showing the working. Okay. So, you can compute. So, if you would like to obtain the values at higher time level, so for example, this is whatever values we have obtained, this corresponds to j equals to 1. If one wants corresponding to j equal to 2, we can use this computed values and compute at j equals to 2. So, we can do the march past like this, okay, with time step. So, this is an implicit scheme. Okay. So, now let us look at a scheme where the derivative boundary conditions are given. I mean not in the scheme, of course, the boundary conditions involve derivatives. So, accordingly the endpoints are also to be considered as unknowns. Okay. So, let us look at example 2. So, I am not writing the problem formally. So, this is initial condition and boundary conditions. So, variety of ways, for example, earlier we were writing x comma like that. So, this is another way. So, is equals to u of course at. So, the same thing we can write at 0 comma t is equals to u 0 comma t. Okay, both mean the same. So, another is x equals to 4 is equal to 0, okay, and say given h equals to 1 and lambda equals to 1 by 4. So, that means accordingly we compute for the next time step, which is one can compute delta t from these two values. Okay. So, obviously you have derivative boundary conditions, hence if you look at the grid, so the solution needs to be obtained even at the end points, okay, because this becomes also an unknown, right. So, let us look at the explicit scheme in this case. Okay. So, u I j plus 1 okay. So, this is explicit scheme. However, in the light of endpoints also being unknowns, this is supposed to be valid at all the grid points. Okay. 1 2 3 4 0 1 2 3 4. Okay. So, now let us look at our initial condition, then look at the boundary condition. So, this is initial condition. So, dou u by dou x equals to u at, so this has to be. So, first let us discretize this. So, if you discretize, see this is dou u by dou x at 0 comma t is, so we have to write at all j. So, this will be, let us approximate this by two h. Okay. So, this not implies. So, this is a discretization we are considering. Accordingly, the condition of u at x equals to 0 become, this is x equal to 0. So, u 1 j and here we get u minus 1 j is equal to 2 h u 0 j. Okay. And the other condition, x equals to 4. So, this corresponds to, so I is 4, u 5 j minus u 3 j equals to 0. Okay. So, we have unknowns at 0, 1, 2, 3, 4. If you recall, if you run at I equal to 0, here we are going to get u minus 1. So, this is a fictitious value. However, we have one equation involving this fictitious value. Similarly, if you run this equation at I equals to 4, we are going to get another fictitious value at the other end, and we have an equation involving this fictitious value. Okay. So, let us A, B. Okay. So, let us run equation A at I equals to 0. So, equation A at I equals to 0, this will be u minus 1 j Okay, this is I equals to 0 minus 2 u 0 j plus u 1 j. Okay. However, C implies u minus 1 j is equal to u 1 j minus 2 h u 0 j. Okay. So, the above equation becomes, say this is a prime so for u minus 1 j. So, we are eliminating the fictitious value. Okay. So, this is a fictitious value and we are eliminating using this equation. So, 1 u 1 j and we get, and our equation h is 1. So, this is minus 2. So, this will be minus okay. So, this is the equation which we have to run at each grid point. Okay. So, accordingly, for I equal to 0, we have, remember we have other and also we have a fictitious value, okay, u 5. So, that needs to be eliminated when we write the equation for I equals to 4. Okay. So, this I equals to 0 will be I equals to 0 will be j plus 1 by 4 then I equals to 1 I equals to 1 will be okay. So, we write down all the equations. Then so this is routine. Now comes the other end point. So, here when we write down, we have the other fictitious point which is this. However, we have u 5 j equals to u 3 j. So, this is our equation number is D. So, this implies so now if you see the system of equations, these 5, they do not involve any fictitious value. Okay. So, they do not involve any fictitious value. So, now we have to start feeding the initial values to compute at the next time level. So, that means we fix j equals to 0 and compute the values at j equals to 1. So, if we do that, j equals to 0, j equals to 0 will be so this can be computed. Now, it would be better to write the corresponding initial and boundary conditions. We have ui 0 is 10. Okay. So, accordingly we have 10, this is valid for I 0 to 4 because endpoints are also unknowns. So, this 10 so this would be minus 20. Okay. Then u 1 1 so we have written the values. So, this will be u this is corresponding to I 1 and j 0. So, this will be zero, so this will be u okay. So, we can compute this comes out to be 10 u 3 1 u 3 1 will be u 3 0 this will be 10 and finally u 4 1. Okay, you can compute. So, this is the derivative boundary condition case. Of course, here just to make the calculation simple, I have considered explicit scheme, but if it is implicit then you further get a system of equations and then you have to handle the system. So, two issues, one is if the scheme is implicit you have to handle the system, and if you have derivative boundary conditions then you get fictitious values due to the end points. Okay. If you run the corresponding discretized equation at the end points, you get the fictitious values which one has to remove using the derivative boundary condition discretization. Okay. So, now let us discuss an example where consistency can be understood. Okay. So, this example is displaying consistency. Okay. Suppose this is approximated by this is j minus 1. Okay. Suppose this is approximated by so this is I plus 1 j, the I j plus 1 and j minus 1 and j. Okay. So, now we would like to based on the error expansion, we would like to check the consistency of this approximation. Okay. So, expanding the terms, we have usual expansion. So, I am just doing one. So, this is with respect to t. So, u I j plus k. So, this is at so similarly other terms. Okay. So, now if we do that, so it is an exercise you must try. T I j is I mean all of them are evaluated at this point. So, you have to expand and make sure that we get this. Then let us look at case 1 where k is lambda h. Then as h goes to 0, T I j goes to, you can see as h goes to 0, T I j goes to so this is the first term, plus two lambda by h square plus lambda square. Okay. So, if k is lambda h, then so this term goes to 0, this is 0, and we get these are the terms, okay, which we have to address. Then when alpha is not equal to half, 2 alpha minus 1, 2 lambda by h square, this goes to, this blows up, okay, right. Then when alpha is half, Tij goes to, so this term goes to 0. So, the non 0 terms, this is x square plus lambda square, okay. So, therefore, this is t square, okay. So, therefore, what is the net conclusion? So, you expand, then if this case k is lambda h, so you substitute, then take limit h goes to 0. So, you can see this has to be taken in two different cases, when lambda is half and lambda is not equals to half. When lambda is not half, this blows up, whereas when lambda equals to half, t goes to this plus the other terms. Okay. So, which means for us, which means the given scheme is consistent with so this is the conclusion. Okay. So, this implies the scheme given is inconsistent with, this is our given equation, always, because this is the given equation. However, in one case when lambda alpha is not equals to half, one term blows up, whereas when alpha equals half, the error is going to this term. So, if this is 0, then there is a corresponding error which is contributing from the next non-zero term. So, that means in the sense the given discretization when alpha equal to half is consistent with this equation, not with this equation. Okay. So, now let us see this case. Okay. So, in this case Tij goes to then alpha not equal to half consistent with, because you have other terms. So, when alpha not equals to half, the equation is consistent with some other, the discrete scheme is consistent with some other equation. What is that equation? You club dou u by dou t 1 plus 2 lambda 2 alpha minus 1 whereas when alpha is half, consistent with okay. So, this tells the verification of a consistency. So, in case 1 when k is lambda h, we have seen the one of the non-zero term blows up in the limit h goes to 0. So, that means definitely error is not bounded. So, consistency does not arise, okay. Whereas it is no longer consistent. Whereas in the second one when k equals to, even when k equals lambda h, if alpha is half, then it is consistent with some other scheme, okay. So, whereas in k equals lambda h square, so for alpha not equals to half, it is consistent with some other scheme, whereas when alpha equals to half, it is consistent with the given parabolic equation, okay. So, that is how one verifies consistency check. So, now let us look at another example where a slightly different equation. I mean, you have standard equation every time we are considering dou u by dou t is dou square u by dou x square, but let us consider equation where you have a first derivative involved with respect to the space variable and then also derivative condition. Okay. So, let us look at it. So, this is our equation. So, this is the initial condition and boundary condition. Okay. So, it is slightly different from what we have been considering because of presence of this term. Okay. Now, this presence of this term creates a slight trouble because our domain is okay. So, as you can see at x equals to 0, there is a slight difficulty with this term. So, these are for simple cases, we are choosing such lambda, so that the calculation becomes simpler. Now, at x equal to 0, okay, consider this term. So, there is a singularity. So, we have to take limit So, this goes to so therefore, the equation reduces to so there is 1 and 2. So, this is okay. So, this is at x equals to 0. So, this is the set we have to use for discretization. Okay. So, let us look at it. So, this implies so this is forward time, this is central second order. Okay. So, at x equal to 0, because of x equals to 0 discretization, we got this fictitious value. Okay. So, this is similar to right. So, since we had to discretize the equation at x equal to 0, we got a fictitious value, right. So, now we have at x equals to 0, dou u by dou x is 0. So, this is our given boundary condition. So, this implies right. So, this gives our equation to be so I have taken this to the right 3 lambda. So, u minus 1 I am going to eliminate. So, we get okay. So, this is and since our in our present case lambda is 1. So, therefore, so this is a say A. Now, we have to discretize at x equals to x not equals to 0. So, our equation given equation is so we discretize two by x. So, this will be I h okay. So, we have to arrange the terms. So, here there is 2 get cancelled, right. So, we have when k goes there, this becomes lambda. Okay. So, we have terms taking common okay. Then so the given problem contains, if you see, only one derivative boundary condition. So, that means only at x equals to 0, whereas at x equals to 1. So, this is known. Okay. So, for all time level, so this is u is 0. So, therefore, the number of unknowns are x 1 is 1 by 4, x 2 is half, x 3 is 3 by 4. So, the number of unknowns are 1, 2, 3, 4 only. Okay. So, we have this, then u equals to 0 at x equals to 1, this implies u 4 j equals to 0 and u of x 0 is 1 minus x square, this implies u I 0 is okay. So, now we can run the equation j equals to 0, sorry. So, u I 1, in fact lambda is 1, we can drop. So, this is explicit. Okay. So, this one and we can call this is B. So, these two we have to, this is our A, this is due to at x equal to 0 and this is x non-zero. Okay. So, that means I 1, 2, 3. So, this is valid for 1, 2, 3. Okay. So, maybe you can run the equations and get explicit values, which is not very difficult. Okay. So, as you can see, this equation contains a term which is a singular at x equal to 0. So, we have taken limit, in the limit it is well behaved because we use a L'Hospital rule and then we got the derivative, second derivative. So, at x equal to 0 the equation behaves in some sense and for other values it behaves in other sense, and then also if the derivative boundary condition is given at only one end, definitely the corresponding fictitious value would appear only on one side, and for the other side we do not have any other fictitious value. Okay. So, I think more or less you got some idea how to use derivative boundary conditions and also how to check the consistency of a given discretized scheme. Okay. So, now let us see how we proceed in the remaining lectures. Until then, thank you, bye.